Hello everyone, I am Chiara Labanti from the Center for Processable Electronics at Imperial College London, and today I will present my research on the stability of organic solar cells and how it can be improved by molecular engineering of non-Fullerene acceptors. So, as we all know, the field of organic solar cells is growing very fast, and lots of research effort is put on the increase of efficiency of devices. But another key requirement for commercialization is the extension of lifetime of devices. It seems that some of the most promising candidates for high efficiency solar cells are not, unfortunately, also stable. So, for example, PM6Y6 system is not very stable in itself. We know some techniques to increase the lifetime. So, for example, the thermal treatment or ternary blending, but this would rather complicate the fabrication protocol. So we need to find an intrinsically stable donor acceptor system. At this regard, it seems that the ITSC family is quite promising. We know some degradation mechanism involved. So for example, the creation of light-induced traps, mobility degradation, and also the morphological instability. But it's still not very clear how these are related to the intrinsic molecular structure of non-Fullerene acceptors, and in particular, ITAC families is very sensitive to the fine-tuning of the molecular structure by N-group engineering, for example. So in this study, we are combining two different routes of molecular engineering, and we are characterizing 4 novel non-Fullerene acceptors and systematically understand the relationship between the molecular structure and the stability. We use the selenation as a tool to engineer the core of the molecule. We substitute the sulfur with the selenium either in the inner or outer core sites. Selenium is known to increase the quinoid resonance, the absorbance, and also to tune the packing and intermolecular interactions, but little is known in terms of stability. Moreover, we use the methylation in the N groups, which is known as beneficial for the open circuit voltage, and we want to understand the relationship between core and N group engineering and the stability of devices. In terms of efficiency of neat devices, we don't notice strong differences across the NFAs, but however, the outer selenium is beneficial for fill factor, the methylation is beneficial for open circuit voltage. So overall, outer selenium methylated is giving the best efficiency around 10%, which is promising. But however, the most important and interesting differences across the NFAs are emerging while testing the lifetime. So by testing continuously in light for hundreds of hours the devices, we can see very clearly that the outer position of selenium is much more stable than the inner, and also the methylation is strongly increasing the lifetime. So overall, outer selenium methylated is giving an exceptional lifetime. Around 95% of the original efficiency is retained after 450 hours of operation in light. And at this regard, the decay of short circuit current is the most important factor. And also the fill factor is playing an important role. So the fill factor is in general decreasing in light, but for the outer selenium methylated is rather increasing by around 5% in the initial stage of degradation. So we want to understand what are the mechanisms involved in degradation and what are the intrinsic relationship with the molecular structure. So we start characterizing the molecule by DFT simulation, and we see that the outer position of selenium is acting as a conformational lock. So the more extended, diffused orbitals of selenium are forming a non-covalent bond with the oxygen in the side chain, in the N groups, and this would lock and rigidify the molecule. And this is mirrored in the solid state films in a lower presence of trap states, so a higher conformational and energetic order. And it's interesting to draw a parallel with the recent observation we published from our group on the Y6. So also Y6 is showing an exceptionally low amount of trap states in thin films. And this is resulting for Y6 in a very high intrinsic stability. So this is also very promising for our ITSE derivatives with selenium substitution in the outer position. Another observation from simulations is the analysis of charge distribution over the molecule, and we see that the outer position of selenium is optimizing the charge delocalization in the core, even reaching the non-conjugated side chains, and the methylation is avoiding excessive charge accumulation in the N groups. So these two routes of engineering are optimizing the charge distribution over the molecule and ensure more possibilities for effective intermolecular interactions in the solid state. So this is resulting in very interesting characteristics in the solid state packing, as we are going to see. So from the optoelectronic properties of thin films, we can say that the outer selenium and the methylation are improving the packing and the crystallinity. So there is a red shift in the absorbance, and also the X-ray data are indicating a much stronger crystallinity for the selenium out and the methylation. A stronger crystallinity both in the acceptor but also in the donor domains in blend, and in particular selenium out methylated show a very versatile and strong intermolecular interaction between the molecules. And this also has outcomes in terms of donor acceptor separation in the bulk heterojunction. So for the outer selenium and the methylation, we have a larger phase segregation, a larger domain size, so a weaker quenching in the photoluminescence in blends, and a longer exciton lifetime. So this is important, as we will see, for the morphological stability of bulk heterojunction. So what are actually the mechanisms involved in the photodegradation? One of them is for sure the degradation of the molecules themselves, so the chemical degradation of the molecule. We see that there is a bleaching in the absorption, so a quenching in the chromophore, and also a bleaching in the vibrational modes, the peaks related to the vibrational modes of the molecule observed from Raman spectroscopy. And we see a degradation both of the non-Fullerene acceptor but also of the polymer. So these mechanisms, however, are much more limited, more controlled for outer selenium and methylation. So it means that the NFAs are intrinsically more stable, but also that the intermolecular interactions are also stabilizing the polymer in the blends. And for outer selenium methylated, we even observe this interesting red shift in the polymer peak in the absorption under light, which is related to a mild reorganization and optimization of the polymer domains morphology to give the increase in the fill factor observed for devices. Another mechanism involved in the photodegradation is the morphological degradation. So by observing the recovery of photoluminescence under light, we can say that there is segregation, phase segregation between donor and acceptor domains. But however, this mechanism is much more controlled, limited when the selenium is in the outer core sites and upon methylation. So in this case, we have initially less intermixed domains, so larger domain size and stronger crystallinity, and this is optimizing the morphology already before degradation, and this avoids further detrimental phase segregation and morphological changes. So to sum up, we systematically investigated the impact of two core and N-group molecular engineering routes for ITIC derivatives, the impact of these on the photostability of devices, and we can say that the combination of selenium substitution in the outer core region and the methylation are very important to rigidify the molecule, to optimize the charge distribution over the molecule, and this would result in stronger intermolecular interactions and better crystallinity in the solid-state packing, which are crucial to control both the chemical and morphological degradation mechanisms, and also to optimize the packing in the polymer and to make also the polymer more stable towards photodegradation. So I hope this piece of research is giving some general guidelines for the design of stable non-Fullerene acceptors for organic photovoltaics. And with that, I would like to conclude and to acknowledge all our collaborators, and especially thank you very much for your kind attention. Thank you.